So hello everyone, welcome back to PC 301, and we are here with the final day of the workshop. Thank you for sticking around. And we start with our first session. We have with us once again Professor M.S. Ramanujan from University of Warwick, and he'll be giving the final talk on Lossy Kernelization. So thank you once again, and over to you now.
Many thanks, Prithika, for the nice introduction and again for the invitation. So the agenda for today's talk really is to pick up where we left off. And as I promised, I'd give a slightly more involved approximate kernel in today's talk. And what I hope is that even if you may not take away the whole algorithm, hopefully there'll be a few pieces that you can keep in mind and that could prove transferable in some of your own work. And in the second half, I'll spend a little bit of time talking about lower bounds and why this direction is not all hunky-dory. There are also very simple problems that turn out to be very difficult, in fact, provably difficult. So let me begin. So I'd like to begin by recalling the notion of PSAKS. So this is a special type of an approximate kernel, or rather it's a family of approximate kernels, really, because for every fixed epsilon, what I'm asking is for a pair of algorithms. There's this reduction algorithm, which, as we mentioned earlier, should run in polynomial time and output this instance I prime k prime. And there should be a polytime solution lifting algorithm that takes any C approximate solution for I prime and turns it into a 1 plus epsilon times C approximate solution for I. And of course, the size of I prime and the value of k prime should both be bounded polynomially in K. And as we saw towards the end of the last talk, this dependence, this polynomial in K could have various types of dependence on epsilon. But for now, we are not really interested in what the specific dependence is, because epsilon is fixed, they're all polynomial. And what I would like to do today is zoom in to this specific family of graphs. These are what I call F deletion problem, family of problems, sorry. So these are what I call F deletion problems. You would have already seen either this family directly, or you would have seen various instances of this family of problems in the last week. So in general, so let F be a fixed finite family of graphs. And in the F deletion problem, what you want is you're given an underrated graph G and a number K, and the question is this graph K vertices away from being F minor free? So can you delete at most K vertices so that the resulting graph does not contain any graph in F as a minor? Now, this abstract problem is very fundamental in this area, primarily because it can be easily seen to generalize many well-studied problems. For instance, if I take my family F to be only a single edge, then making sure that my graph does not contain an edge as a minor is the same as saying that the graph must be independent, must be an independent set, i.e. vertex cover. Similarly, if my family F only comprises the triangle, then what I want is to eliminate all cycles from my graph, in which case this problem is precisely feedback vertex set, and so on. And as you would have already seen in previous talks and in what Mike spoke about yesterday, so starting from Robertson and Seymour's work, there have been a lot of very interesting algorithmic results inspired by and aimed towards resolving various questions regarding the F deletion problem. And the same holds also for polynomial kernels. So this is actually a very rich subdomain where you have a lot of very interesting structural results, and new algorithmic techniques have been introduced. in an effort to answer various questions around F deletion. Now, let me tie this back to what we saw yesterday, which is the case of the connected vertex cover problem. Now, what we did there was we took this very natural vertex cover problem, which you're all quite familiar with, and then we asked, okay, what if I insisted that the vertex cover that I care about also induce a connected subgraph? And as you already saw, this made a massive difference. And you could naturally ask the same question for the F deletion problem in general. So I want an F deletion set, so a set whose deletion eliminates all F minor models from my graph, plus I insist that this set should induce a connected subgraph. And again, various special cases of this abstract problem have already been well studied. For instance, connected vertex cover, connected feedback vertex set, and so on. But in general, there are various FPT results that have been explicitly proven or can be inferred from existing knowledge, but there isn't really a systematic research program devoted to this particular problem. And especially when it comes to polynomial kernels, there is a very natural reason why there is the lack of such a program. So already for the connected vertex cover problem, as we saw earlier, it is too approximable and there's an exponential size kernel, but we know that there is no polynomial size kernel. So that already killed the idea of studying kernelization for connected F deletion in the crib. But now that we have this new perspective, that of approximate kernelization, it makes sense for us to revisit this family of problems and ask, okay, now that we have this little window into a new world, does it make sense to study connected F deletion in this world? And a promising starting point is this result that we saw yesterday for connected vertex cover that said, yes, the moment you allow some inaccuracy, you are able to dramatically improve your pre-processing power, i.e. obtain a polynomial approximate kernel. And in fact, you could do really well, i.e. get arbitrarily close to 1 when it comes to the accuracy. Now, this is a very good first step. It's a promising first step that provides a meaning to more general questions. For instance, now what about connected feedback vertex set? Could one have an approximate kernel? Could one have a PSAKS even? What about deletion sets to graphs of bounded tree width? Could this have an approximate kernel? Could this have a PSAKS even? And so on. And for all of these problems, the question already makes sense because for connected vertex cover, we know that there is a lower bound of 2 in the approximation ratio, and there is a no polykernel result. So this new program of research naturally appears. And what I'd like to do in most of this talk is describe a PSAKS for the connected feedback vertex set problem. So this will be a bit more involved when compared to the connected vertex cover PSAKS for obvious reasons. But what I'd like to do is, again, address it in the same spirit and talk about the connected feedback vertex set, or rather the feedback vertex set kernel ideas and where they fail and why we need to do something different for, and what can be done differently for the connected feedback vertex set problem. So at a high level, we are going to do something very similar to what we saw yesterday. So given this graph G and K, we are going to come up with a polynomial time subroutine that either correctly concludes that there is no connected feedback vertex set of size at most K for the input graph, or it computes a small subgraph, G prime, whose size is bounded polynomially in K, and then argue that it's sufficient for us to zoom in onto G prime, or rather focus our attention on G prime. And if you come up with any good approximation in G prime, that can be turned into a good approximation for G efficiently. So this is essentially what an approximate kernel needs to do. So towards computing G prime, what we are going to do is we are first going to decompose G in the way that's described in the picture. So I'll zoom into this picture, so don't worry if you're not able to see things clearly. And once we decompose G, we'll start staring at each piece of the decomposition and try and understand what role each of these pieces play in relation to some hypothetical solution that you have in mind. So I hope the high level approach is clear. So now let me talk about the decomposition itself. This is nothing very new. It's based on what is already known for kernelization for feedback vertex set. So it's very closely related to what's already there. So here is the decomposition. So I have three vertex sets, H, Z, and X. Cumulatively, they're all small, i.e. size some poly K. And the important thing to note is that each of these sets has some further meaning. So H, for instance, I promise, is part of every feedback vertex set of size at most K. So this is the analogous version of the high degree vertices for vertex cover. You know, if you had high degree vertices, you knew that they had to be part of the vertex cover. So there is an analogous notion using a notion of flowers that works for feedback vertex set, and that's where H comes from. Then the remaining vertices, I partition them into two. So one set are those vertices that could have neighbors in H and Z, but they don't have neighbors in X. So these are essentially vertices that I call type 0 and type 1. Vertices, essentially, these are just vertices that have degree at most 0 or 1 into Z. So they could have any neighborhood into H, I don't care. They have no neighbors in X, and they have degree at most 0 or 1 into Z. And then type 2 is everything that's left. But we will be able to show that in this decomposition, again, type 2 vertices also don't have any neighbors in X. But each tree in the type 2 set actually has exactly two neighbors in Z. At this point, I realized that I did not mention one very important thing. This set H, Z, X together, they form a feedback vertex set, which is why everything outside is something I kept referring to as trees. So that's important. So each component in this type 2 graph is a tree, and each tree sees exactly two vertices of Z. They see some arbitrary number of vertices in H and no vertices in X. Now, I'm not going to go into detail about how this decomposition can be obtained, but I'm of course happy to talk to you at the end of this talk, or just let me know if you have any questions about how this decomposition can be obtained. Okay, so this is what the decomposition looks like. So there's a small set in between, which is a feedback vertex set. So it's an approximate feedback vertex set. If you remove it, all you're left with is trees. I partition them into two types, type 0, type 1, and type 2, with these properties. Now, why am I doing all this? What can I infer from this structure? Well, I claim that really type 0, type 1 vertices, they don't really play a role in hitting cycles. Why is this the case? Well, look at the set H. I know that H is going to be deleted no matter what. It's part of my solution. So if my goal was to hit cycles and I delete H, can I have any cycles that then pass through type 0 or type 1 vertices? No, because they're all trees and each connected component there sees exactly or at most one vertex outside. So if you enter that connected component, you're not going to leave. So there cannot be any cycles passing through them once H is deleted. So once I add H to my solution, the only role these vertices can play is that of providing connectivity. So this is similar to the role that the independent set vertices were playing in the case of connected vertex cover that we saw yesterday.
Hi, MS sir. Just
Yes.
one quick clarification. So type
Yes.
0 and type 1 vertices, all of them have means no vertex of type 0 or type 1 have no neighbors in X at all?
Correct. The picture is a bit misleading. You're correct, Ditapriya, if that's what caused the confusion. But no, they do not have any neighbors in X at all.
Okay, also type 2 vertices also have no neighbors in X at all.
Correct.
Okay, I see. Okay.
Yeah, okay. Yeah, sorry about the misleading picture showing an edge between type 0, type 1, and X. Okay, so type 0, type 1 vertices only play a role in providing connectivity. They're not interested for hitting cycles once H is removed. But type 2 vertices are more intricate. So they could potentially provide connectivity while also performing uh, some cycle hitting duties. But what we are going to do now is zoom into each type 2 component and try and understand in what way could they hit cycles. Can the cycles hit by vertices in type 2 be of any kind? Or are these very restricted type of cycles? And it will turn out to be the latter. So let's zoom in to this some arbitrary type 2 component. And as mentioned earlier, there is no neighborhood, there are no edges between the component C and X. There are exactly two neighbors in Z. And there could be some arbitrary number of neighbors in H. Okay, now because it has exactly two neighbors in Z, and the type 2 component itself must be a tree, this is what the component must look like. So there must be an A-B path where A and B are the neighbors of the component in Z. And the component C comprises this A-B path minus A and B, and a bunch of trees hanging from this A-B path. I know this is not very formal, but I hope I'm conveying the description reasonably accurately and assisted by the picture, hopefully. Okay, so now if I look at the vertices on this type 2 component C and see how they can hit cycles. Recall, I only need to consider cycles disjoint from H because H is going to be deleted anyway. So once H is deleted, what do cycles look like that pass through this component C? Well, any such cycle must enter this component through A and exit it through B. This is definitely necessary. And then it must comprise this entire unique AB path, and it cannot take anything else because everything else is a tree. So it can never come back to this path. So this brings us to the next observation, which is that if you look at the trees that are hanging from this path, they don't play any role in hitting cycles. They only play a role in providing connectivity. So in that sense, they are sort of like type 0, type 1 vertices all over again. So any cycle must pass through both A and B, so it must just go through this entire AB path. Okay. Now it's the vertices on this AB path that could be difficult to handle because these could be the vertices that could hit a cycle and they can provide connectivity between various vertices in the solution. So that's where our difficulty really lies. Okay. Now the question remains, well, okay, which vertices? Like different vertices on this path could have different utility, so to speak. So it's not clear which ones are more useful than others. But one thing I would encourage you to notice, if you haven't already, is that as far as hitting cycles goes, it doesn't matter which vertex you pick on this path. They will all hit any cycle that uses this subpath. So in one aspect, all these vertices are equivalent. What really distinguishes them is how well they can provide connectivity between various other vertices. So I hope I've spotlighted the main remaining difficulty, and it's that what we'll resolve shortly. And before that, I'd like to take a very short digression and recall this very useful lemma of Borchers and Do. And this is one piece I hope that you'll be taking away, even if you don't grasp the entire algorithm today. So what Borchers and Do showed is that let's say you have a Steiner tree instance, so you have a bunch of terminals, and the goal is to connect these terminals using as few edges as possible, or if it's a weighted case, as light a set of edges as possible. Now, if you give me some error parameter, call it epsilon, what I can argue is that if I fix some optimal, so there is an optimal Steiner tree that I can come up with, such that if I then go over all some p of 1 over epsilon sized sets of my terminals, so the terminal set is unboundedly large to begin with, but if I go over each small subset of terminals and store an optimal Steiner tree for these pieces, and then take the graph induced on all of these little Steiner trees, I can come up with a Steiner tree that is not too far from this optimum that I had in mind. So there is a way to come up with a subgraph that contains a 1 plus epsilon approximation. And the useful thing is that the subgraph can be constructed by just going over constant sized subsets of terminals, and for each constant sized subset, build an actual optimal Steiner tree, which we can do in polynomial time. And this lemma is very useful for us because that's really what we want when it comes to addressing the connectivity question. So what are the vertices that the vertices on the subpath would provide connectivity for? Well, there are vertices in H, then the vertex A and B. And these are potentially vertices that would need to be connected in the end. So I would go over all constant sized subsets of H union A comma B. And for each such subset, I will store an actual optimal Steiner tree that is sitting inside this component C. And I only care about Steiner trees that have size at most k. If it's too large, I just ignore that particular subset. So this way, I have a poly k number of possible subsets. For each subset, I have a order k sized tree. So overall, my subgraph that I mark in this procedure will have size poly k. And we'll see that this is really sufficient. The remaining vertices are pretty much irrelevant. So whatever I wanted to achieve, I would have achieved just within these poly k vertices that I had marked. The important point being that I'm allowed to make an epsilon error, and that is very crucial. Now, this Steiner tree lemma alone is not sufficient. You also need a slightly different variant for the group Steiner tree problem. But this is very similar to that. And indeed, you can actually reduce this lemma to the previous one. So the previous lemma is actually a subroutine in the proof of this lemma. So the point here being that maybe I won't be connecting just H, A, and B, but there could be one more vertex on this path which I want to connect, right? Because this vertex could be useful for hitting cycles. So I also have a group comprising all the vertices on this path just to cover this possibility as well. So the primary takeaway in the last two slides is this nice approximation result for Steiner tree. And in fact, you can think of it as a PSAKS for Steiner tree that's been around since '95. So here is another example where people have thought of this object, not necessarily from a kernelization point of view, but from a different perspective, and they stumbled on this very natural object. Okay, so now that we have marked these sort of relevant vertices, well, what do we do with the rest? I mean, we still need to reduce our graph. What would a natural reduction rule be? Well, if you look at vertices that are hanging in these trees that are not marked, you can just delete them, because since they are not marked, they are not useful for connecting, and they are anyway not useful for hitting cycles. Now, what about vertices that lie on this subpath, AB subpath, that have not been marked? Well, I can just contract unmarked portions of the subpath, and I still won't lose anything. So I won't have broken any cycles because the cycles can still pass through this contracted subpath. And since they're not relevant for connectivity, I won't have lost anything in that aspect either. So that would be the reduction. So this would shrink each type 2 component to poly K size. So coming back to this, this decomposition, what this allows us to do is shrink each type 2 component to poly K size. And I can take the entire set of type 0, type 1 vertices and apply the same reasoning to get a one-shot reduction that compresses all of them to poly K size. So I won't be doing this for each component, but for all of the type 0, type 1 vertices in one shot. And there is a reason for this. One is, well, I mean, it's correct to do this. And the second thing is the number of connected components in type 0, type 1 could be unbounded. But the number of components in type 2 is bounded by a polynomial in K. So this also can be proved. And because of that, if I shrink each connected component to size poly K, and there are only poly K, many of them, the number of vertices left in the type 2 components would still be poly K. So this way, we would have reduced the number of vertices to poly K overall. So the type 0 union type 1 becomes poly K. The middle piece is already poly K, as I mentioned, and the bottom now becomes poly K because of our reduction rules. So the entire approximate kernel looks like this. So I start with GK, and in polynomial time, I compute this decomposition or conclude that opt is too high. Once I compute this decomposition, I use these marking rules to sort of identify the relevant vertices. And for the irrelevant vertices, I have various reduction rules. Either I delete them or I contract some paths. And this way we would be left with a graph G prime, which is not a subgraph. It would be a minor of my original graph, really. So this this is a summary of the entire PSAKS for the connected feedback vertex set problem. I realize that I've swept quite a few details under the rug here. So feel free to have a look at the paper. So this result was in an ASA paper last year. But of course, you're welcome to ask your questions here as well. So I'll pause for a few seconds in case there are any questions. Okay, so now that we have this result for connected feedback vertex set, there is a further set of questions you could ask, right? I mean, you could now go from feedback vertex set to what about graphs of bounded tree width? Well, there we actually don't know whether there is a PSAKS. So the best that I know is a 2 plus epsilon approximate kernel of polynomial size, of course, which is still interesting, but getting a PSAKS seems non-trivial. And of course, the ultimate objective would be to push this all the way to the connected F deletion problem for any fixed F. But that is, of course, quite a long way away, and we need to understand many other easier families of forbidden minors before we get to something at that level. So if you're interested in open problems, so here is one. So a PSAKS for connected deletion to bounded tree width graphs for any fixed tree width. Okay, so that's what I wanted to say about PSAKSs. Again, before I move on, let me quickly comment on the form of this PSAKS. So the size of the PSAKS is k to the order some 2 to the 1 over epsilon. So the question there is, I mean, can you do better? So can you get a f of 1 over epsilon times k to the c sized kernel? Such a question remains open even for connected vertex cover. So that would probably be a good place to start before addressing connected feedback vertex set. If one can show that such a thing does not exist, then that would definitely be very interesting. About the running time in this algorithm. So for connected vertex cover, it was truly polynomial time. So there were no exponential dependence on 1 over epsilon hidden anywhere. But here, there is an exponential dependence on 1 over epsilon hidden, mainly because if you remember, when applying the Steiner tree marking, you need to go over a bunch of subsets of size 1 over epsilon. So there is a so there is a k to the 1 over epsilon dependence there, really. It would be great if that can be avoided and it can be truly polynomial time with no 1 over epsilon in the exponent anywhere. That's another question that I would like to throw out there regarding this. Okay.
Hi, MS sir, just a quick clarification. Very recently, something you said about dependence of epsilon in the exponent. So for this algorithm, so this entire preprocessing algorithm, so the dependence of epsilon in the exponent, is it something only on the is it something like k power 1 over epsilon, something like that?
Yes, in the running time.
But there is nothing like n power 1 over epsilon or anything like that.
You're correct. No, we don't. It's
but
k to
maybe,
the 1 over.
I don't know. Maybe it may be possible to justify that this also means, so this particular running time you have, this also imply a time efficient PSAKS. Maybe if the input size itself is smaller than something, I don't know if I am.
That's actually a good point. But what I was asking for was something similar to the to the connected vertex cover setting where, I mean, it's just polynomial. There is no 1 over epsilon anywhere.
Okay.
Does that make sense? I see what you're saying. Yes, indeed, you can get from k to the 1 over epsilon to f of 1 over epsilon. Is that what you mean?
Yeah, I mean, so I mean, given this thing, you can prove that this PSAK is also time efficient. I mean, I think did you mention this term before or not?
No, I have not mentioned this time before. This term. But yes, Deeptapri, I agree that it can be made time efficient. Yes.
Okay. Okay.
Yes. Okay. Are there any other questions? So I haven't been checking the chat, so I'm assuming that Pratibha would stop me if there are questions.
Yeah, I'm keeping a check.
Thanks.
So MS,
Okay. Yes.
You mentioned deletion to bounded tree with graphs. Without the connectivity restriction, what is known? Or is that?
It has polykernel.
Oh, okay.
Yes.
Okay, yeah, sure.
So this planar F deletion for, yeah, so it's sort of, it's a special case of planar F deletion. So,
okay.
Sure. Okay. So thanks for the nice questions. So now moving on, what I'd like to speak about briefly is about lower bounds. So I won't be giving lower bound proofs, but what the goal really here is to tell you that, well, there is a lower bound machinery. It's somewhat in its infancy, so to speak. So there's a lot of interesting work to be done here. To begin with, recall these two statements that I talked about yesterday. Now, these two statements already give us a way to rule out alpha approximate kernels. So, for instance, if you have a result that says, under whatever hypothesis, this problem does not have an FPT alpha approximation, then you also know that under the same hypothesis, you don't have an alpha approximate kernel of any size. The first one, again, so ruling out an alpha approximate kernel of constant size is not terribly interesting, but in principle, you can make such a claim based on non-approximability in the classical sense. So you already have a very rudimentary approach to rule out alpha approximate kernels, but what we'd like to do is now bring in existing machinery that we already have for kernel lower bounds and combine it appropriately with the machinery that we have for approximation lower bounds and see if we can come up with a lower bound machinery that combines these two aspects in an appropriate way. So ruling out some C approximate polynomial kernels essentially involves, or rather, it's inspired by ruling out polynomial kernels using this notion of cross compositions and ruling out C approximations using gap creating reductions. These are two classical approaches for lower bounds in these two domains. So the natural question is, well, is there an appropriate notion of gap creating cross compositions? And as it turns out, one can come up with an appropriate notion of gap creating cross compositions using which you can rule out approximate kernels for a few problems. So at a high level, it's again very similar to cross composition. So you have a bunch of instances of some NP-hard problem. And what you want is a polynomial time algorithm that now outputs some instance of your problem, the problem that you want to cross compose into, the problem for which you want a lower bound. So this routine, it outputs some number R and some instance of this, of let's say a maximization problem that you care about. There's an analogous version for minimization problems, such that, well, again, K prime should be bounded polynomially in the largest of these inputs and log T. T is the number of these inputs, as earlier. And remember where earlier you were saying that, the new output instance is a yes instance if and only if one of these was. What we want to say is something like the new instance has a large opt because it's a maximization problem, precisely when at least one of these input instances is a yes instance of L. And on the other hand, if none of these instances are a yes instance of L, then the instance that I output has a very small opt. Now, this large and small is something that can be formalized in the gap creating language. So this is where we can now talk about alpha gap creating cross compositions, because alpha is the gap that you're creating. So now you're outputting this y comma k prime with the promise that if some xi is a yes instance, then your new opt is at least r. Otherwise, it's upper bounded by r over alpha, hence giving you the gap. Now, why is this useful? Again, you can come up with a composed argument which goes as follows. So if you have an alpha gap creating cross composition from L to your problem P, and hypothetically you have an alpha approximate polykernel for this problem, then you can show using techniques similar to what you've already seen, is that NP is in co-NP/poly. So this is something unlikely. That's the main thing. So to show that an alpha approximate polykernel for P is unlikely, it is sufficient for you to give an alpha gap creating cross composition from some NP hard language L to your problem. And a very simple example of this, or a very simple application of this, is for the longest path problem, which hopefully you've already seen. And longest path is one of the earliest examples that you would see when talking about kernel lower bounds. And as it turns out, even in this new world of approximate kernels, this problem is still very hard to pre-process, i.e. kernelize, even given the fact that you're allowed to have some inaccuracy. So what you can show is that alpha gap long path, alpha gap cross composes into longest path. So alpha gap long path is the NP hard language that we cross compose from. So if you're not familiar with this problem, let me just quickly state what this language alpha gap long path is. So you're given G and K. What we want to say that if G has a path of length at least K, it's a yes instance. And if the longest path in G is less than K over alpha, then it's a no instance. So this is what we want to distinguish between. And so this problem can be shown to alpha gap cross compose into longest path in a quite simple way by taking your disjoint union, really. So that's effectively what's happening here. And that should give you a lower bound for longest path. So again, here is a proof of concept, really, that not every problem can be easily alpha approximate kernelized. Another problem that I'd like to mention is the set cover problem parameterized by the universe size. So again, here we know that there is no alpha approximate polykernel for any alpha unless NP is in co-NP/poly. And the reason why I threw up this problem is because in the classical setting, or rather in the standard kernelization setting, this problem has been a very fruitful source of lower bounds for vast numbers of other problems. So starting from the hardness for set cover parameterized by universe size, we could come up with kernelization hardness for many other problems using an appropriate notion of reductions or polynomial parameter transformations. Now, this raises the question, what would be an appropriate notion of polynomial parameter transformation in this world? And again, there is a very natural notion of alpha approximate polynomial parameter transformations from problem P to problem Q. So it's very similar to what an approximate kernel is. Right? So I want to transform an instance of problem P to problem Q such that any C approximation for this instance of Q can be efficiently turned into an alpha C approximation for the original instance of P. So this was what an alpha approximate polynomial transformation would be. Well, of course, the other boxes need to be checked. For instance, this runs in polynomial time. The parameter size does not blow up by more than a polynomial factor. These are all things that were already there. Now, let's say you have such a transformation. And then suppose that someone gives you a beta over alpha approximate polynomial kernel or compression for Q. A compression, simply think of it as a kernel, but the output does not need to be an instance of Q. It could be an instance of any language. So suppose you had such a thing, then you would be able to compose these two algorithms to obtain a beta approximate polynomial compression for P. So first run this alpha APPT to get to Q, and then you run this beta over alpha approximate poly compression, and your composition will give you a beta approximate polynomial compression for P. Now, if you had that already ruled out, for instance, in the case of set cover, then you could infer something about the hardness of Q. So specifically, if you already showed that P does not have a beta approximate poly compression, and you give this alpha APPT from P to Q, then one can then infer that there cannot be a beta over alpha approximate poly compression for Q. So this is a very natural analog of the polynomial parameter transformations that you would have already seen. So the main takeaway in the last set of slides was that there exists this machinery that is somewhat naturally inspired by existing lower bound machinery in kernels and approximation. There isn't a huge set of lower bound results known, so there are a lot of interesting problems to try here. And that's what I wanted to say in the lower bound segment. So I think I'll wrap up now by reminding you the main takeaways. Well, for one, now you know that a lot of problems don't have polynomial kernels, or we don't believe that they do under reasonable hypothesis, and you've now learned techniques to show that. But now, what these two talks hopefully have given you is hope that that's not the end of the story, and it's that definitely need not be the end of the story. And you can then ask yourself, okay, if there is no polynomial kernel, could there then be an approximate polynomial kernel? And we've already seen quite a few problems for which there are some non-trivial approximate polynomial kernels. The second thing, again, I wanted to remind you that this viewpoint need not be restricted only to problems without polykernels. Even for problems with polykernels, you can ask, okay, what if I now allow approximation? Could I do significantly better in the kernel size? So if there is a k to the little of d lower bound for standard kernel for a problem, whatever d is, ask yourself, what if I only cared about a 2 approximate polynomial kernel? Can I do k to the little of d then, right? Of course, one thing to remember here is that if the problem already has a polynomial time 2 approximation, this question doesn't make sense. So one should always keep in mind this baseline from which you start. What is the best known approximation ratio? What is the best known kernel bound? Based on that, you generate your meaningful questions. And of course, as we just saw, that there is also a low bound machinery. So not every problem must have an approximate kernel. So if at some point you get stuck and you seem to encounter some fundamental obstacles towards designing an approximate kernel, I think that would be a good starting point to think about lower bounds for those problems. Now, of course, as the field has progressed, you would have seen the last few years, there's a lot of interesting technique transfer, cross collaboration between people in parameterized, complexity, approximation, intractability, and so on. So here is another line of research where such collaborations could prove fruitful. And the final thing I wanted to say is there isn't really a very heavy startup cost to getting into this. So all you really need is to have basic understanding of kernels, and then you could pick your favorite problem, think of your favorite parameters, and start asking what would appropriate. Start asking whether there exists an approximate kernels for appropriate values of the approximation ratio and the kernel size, of course. So at this point, I'd like to thank you all for your time, and I'm happy to take any questions.
Thank you for the talk.